Hello, everybody. We are on our final lesson for kinematics already. We are talking about just extension of projectiles. We're going to go a little bit deeper into projectiles. We're going to discuss what happens when an object. In our last lesson, we discussed what happens when an object starts from a horizontal or starts from rest. And now we are discussing objects that are projected at an angle above the horizontal. So we're talking about objects that have an angle when they are first beginning and how we can solve those problems. So same basic principles apply. We just have to consider a few more things. All right, so let's get started. So the trajectory that this object takes is called a parabola. What you see here is that at every single moment, I mean, maybe argumentatively, you could say that this one is the only exception, but at every single moment, there's a horizontal component of the velocity and there's a vertical component of the velocity. And what you'll see, though, is that the horizontal component is constant the entire time. So the horizontal component of the velocity is always constant. And that's because we're ignoring air resistance. So therefore, there's no negative acceleration or positive acceleration on the object in the x direction. It stays the same. However, what you'll notice is the vertical components on the way up seem to be getting smaller to a point where they're zero just for a brief moment at the peak of the trajectory. The y component of the velocity is zero, and then they begin to increase again in the opposite direction, in the negative direction. So therefore, we can say that the y component of the velocity is always changing. And the reason for this, as I'm sure you can guess, is because of gravitational acceleration. Okay, now a couple things to remember, which will just help us to solve these problems as we're about to do them here. The time that it takes for the object to reach the top of its motion is equal to the time that it takes for it to fall back down to the height where it began. Okay, so for the object to go from here up to here is equal to the time it takes for it to go from here down to here. That is extremely useful for us. So the change in time on the way up is equal to the change in time on the way down. Next, the displacement on the way up is also equal to the displacement on the way down. So displacement up equals displacement down. So similar to the time, the displacement on the way up. So the change in its y direction of displacement is equal to the change in its y direction of displacement on the way back down. Now, another one. The initial velocity at the point of release is going to be the same as the final velocity when it reaches the ground. Now, the only thing that we need to consider here that is not the same is that the directions are going to be different, right? Because one will be pointing up and say to the right, and the other one will be pointing down and to the right. So the directions will be different, but the magnitude of the velocity will be the same. So the initial velocity at the point of release is the same as the final velocity when it reaches that exact same height. So Vy here is equal to Vy here, just opposite direction. Vx is always the same. We said that initially. At the top of its motion, the velocity in the y direction is equal to 0 for a brief second because the object needs to change directions to fall back down. So, top of its motion, velocity in the y direction is 0. Okay? And then the last one is that if we're looking for maximum range, this one is maybe a little bit less important than the others, but if we're looking for maximum range, our trajectory should begin at an angle of 45 degrees. Okay, so our initial trajectory should be 45 degrees. That'll give us maximum range. Now, what is range? What does range mean? Well, we discussed what the displacement in the x direction is. The displacement in the x direction, just another word for it, is range. So delta dx, let's write that down here. Delta dx, the term for it is the range. Okay? And so you'll see it down here in part C of this question. It says, what is its range? Well, then you know you're just trying to find delta dx. Okay? Let's even write that down there just so we don't forget. Delta dx. That's what we're trying to find. Okay, hang time is part B, but first off, let's start with part A. Find the maximum height reached by this football. So let's read the question here. A football is kicked at an angle of 50.0 degrees above the horizontal, and it's kicked with an initial speed of 24 meters per second. It says ignore air resistance, and we can just assume that I'm not just gonna throw in an air resistance for you on our first question here. So we're gonna ignore air resistance. And we have to find the maximum height reached by the ball. So the first thing that I'm going to do is I'm going to just take my orange marker here and I'm going to just distinguish what my positive direction and my negative directions are. Okay, so let's make ourselves a little compass looking shape here so we can talk about up, down, left, and right, or forward and back. Let's make up positive, down negative, and we'll make to the right positive, and to the left, it won't be going to the left, so that's not really as important. Positive, we might as well make that positive. Now, we have been given the idea here, let's draw on our little diagram here, that we have got a V1 is equal to 24 degrees. So this right here, what they gave us, that is the 24, sorry, I said degrees, I meant to say meters per second. That is the 24 meters per second. So that's the angle. So that's not really helping us quite yet. It's giving us some information that we need. We are going to need to find V1x, like it has it drawn here. And then it has it drawn up here, but I'm just going to move it over here. So we're going tip to tail, and that is V1y. We have to find V1x, and we have to find V1y. So let's start off. When we're talking about height, we're really talking about the y direction, right? We don't really need to consider what the x direction is. So let's start off by just looking at the y direction. Do we know what we can find what v1y is equal to? Because we have this triangle here, right? We have the hypotenuse is 24, we have the angle is 50, and we know that we're trying to find the opposite. So using what we've learned in class here before, we know that it's just going to be hypotenuse, which is 24, sine theta, and theta is 50 degrees. 24 sine 50. Plug that into your calculator, you should get 18.385. Leave a few decimal places because you're early in the question here. Meters per second, and it's going up. What else do we know here when we're looking at the y direction in a projectiles problem? Well, if we're looking at the y direction in a projectiles problem, we can also assume that we know gravity, right? Because gravity due to acceleration is all that's acting on this object once it leaves the projectile. So, or whatever's launching it, right? So our gravity is 9.8 meters per second squared downwards. And what are we trying to find? Well, we're trying to find height. Range is delta dx. Height is just delta dy, right? It doesn't seem like we have enough information here, but we do. If I come back and I look at this last page here, we have a key piece right here. At the top of its motion, the velocity in the y direction is equal to 0. The top of its motion, in other words, its maximum height. So right here, we'll call it v2y because we're looking at it going up. It's equal to 0. right? At the peak, it's equal to 0. So V2y is 0. And then all that's left to do is find delta dy. That's what we're trying to find. So look at your formula sheets and you'll see a nice looking formula that looks like it'll work perfectly. It'll be V2y squared is equal to V1y squared plus 2a delta dy. Okay, now this is nice because we know that V2y is equal to 0. So we can cross that one out. And now let's plug in let's just look at it as a scalar now because we know our directions, our positive and negatives. So we have 0 equals 18.385 squared plus 2 times negative 9.8 because it is downwards, and we said down is negative, times delta dy. So we need to solve here for delta dy. So basically what we need to do is we need to move the 18.385 squared to the other side. So we will get negative 18.385 squared. And then I end up with that equal to 2 times negative 9.8 delta dy. So we just divide by 2 times negative 9.8 on both sides. And I should get, I'm just going to move delta dy to the left-hand side because that's what we're trying to find, negative 18.385 squared divided by 2 times negative 9.8. And that should give us a nice final answer. We should be looking for our final answer to have 3 sig figs. So our final answer should be a positive number because we have a negative divided by a negative. And if you plug that into your calculator, you should get 17.2 meters up. So there's our final answer. There's our final answer. Now, if I'm trying to find its hang time, basically hang time is the total time it takes for it to go up and then all the way back down. So the key to doing this one is remembering from our last page that it said the time that it takes for it to reach its peak is the same as the time that it takes for it to fall back down to where it was initially released from. So what I'm going to do is I'm going to try to find the time that it takes for it to reach its peak. And then using that same idea or that principle that we talked about in the last page or on the last page, we can then, figure it out in our minds that if delta t for it to reach its peak, delta t up is equal to delta t down, that was on the last page. Well, if they're the same, if delta t up and delta t down are the same, then the total time, delta t, is just equal to 2 times delta t up, right? Because I can say that the total time is equal to t up plus t down, but if t up is just equal to t down, then we have t up plus t up. Another way to say that is 2 times t up. So this is key here. This is really important to be able to use this formula. So let's solve now. Now we can solve. We look at our formula sheet. We know what V2y is. We know what V1y is, and we know what A is. So therefore, I can say V2y is equal to V1y plus A delta t. V2y is equal to 0. And I will just get, if I rearrange this, I will get that I'll move V1y to the other side. So let's do that. So delta t is equal to, we're moving V1y to the other side. So negative, and V1y was 18.3, oops, 1.8 instead of 18. 18.385. We calculate that right off the bat, divided by negative 9.8, because it's down. You don't ever want to get a negative time. So your negatives should generally cancel, or should always cancel when you're talking about time. And you should get 1.876 seconds. So then what we do, that's our T. I forgot to put my little subscript here. That's our T up. That's our T up. So then I take that value and I plug it in right there. And now I can find the total time. So the total time should be equal to 2 times 1.876. So our total time that we're looking for is 3.75 seconds. Okay, we're back. Just had somebody walk into the room there, no worries. Okay, so our last part of the question here is now we need to find the range. So we need to find delta dx. Consider that delta dx, we have no acceleration happening in the x direction, correct? So it's always the same. So our formula is actually a really straightforward one that we use. It is just Vx is equal to delta dx over delta t. And we actually do know what Vx is. We can find Vx way up here. Maybe I'll draw an arrow all the way down here. We can find Vx. It's right here. And it stays the same the entire time, right? So remember, V1y was 24 sine 50. Now, V1x is 24 cos 50, and it never changes throughout the entire question, right? So once we find it here, which if you plug 24 cos 50 into your calculators, you should get 15.427 meters per second, and that's to the right or forward. Well, now we can solve the problem. Now we need to just rearrange this formula for delta dx. So delta dx is equal to Vx delta t. And Vx, I've switched to my scalars here now. Vx is to the right and it's positive. And notice I've replaced V1x with Vx because V1x is equal to V2x is equal to Vx. They're all the same because there's no acceleration. They never change. So Vx is 15.427 and delta t is, well, we just calculated it right up here, 3.75. And actually, if we want to be more accurate, don't take our rounded value from the question above. So 2 times 1.876, 3.752 technically, just to make our answer even more accurate if we need to. So 3.752 times 15.427 should give us 57.88. So it didn't actually end up making a difference. We will still round our answer to 57.9 meters. And we can say, I don't know, I'll say to the right. It didn't really specify a direction. And make sure you put your vector arrow above there because we are looking at a vector now because we have a direction. And there you have it. That is your final answer. We will actually, I said it was our last lesson, but considering how long that one took, we'll have one more lesson just for that last page of the booklet to go over that last projectile motion example together, just so you can get a better idea of how to do those trickier projectiles on your own. So good luck with the practice problems, and we'll talk to you later.